All right.
Goal for using this.
All right, we'll spend the first 2 minutes answering any questions about the homework assignments starting now. I'm just kidding. You guys can spend as much time as you need to talk about the homework assignment. Go next. No. You can use any number of characters. Yeah, the 3 underscores is really just there to indicate, okay, this is a placeholder. Yeah, it's just a placeholder. You can use anything you want in place of the underscores. Yep. Is that the only question?
Yeah.
Okay, okay.
After you store those values with the dot byte, the dot word, the dot long towards the beginning, how do you access those values later? Is there a specific?
Okay, so this is how it works. Okay, so in memory, okay, the first thing you want to do is to kind of go back to the first sample program that I wrote on Tuesday, which is not even a program.
Okay.
Because in that exercise, I kind of show you how to use the X command to look at the memory content, print it out using hexadecimal and stuff like that. So that would be the one useful thing to do. But nonetheless, okay, so if you remember from that example, how did I know where to dump the memory content? Does anyone remember? On Tuesday, the very first sample program that I wrote was just a dot. I cannot even remember. Was it a dot word, a dot int? So something along that line, okay?
Indirect. Indirect.
Say again?
Indirect. Dot indirect.
Dot int?
Indirect.
Okay, indirect. But anyway, I wrote that program, and I used the X command to look at the content in memory. So that would be the first thing that I would check is that particular program. And let's take a look. It is a rare occasion I actually remember what I said in a particular class. Okay, so let's. That's. Yeah, that's useless. The caption is pretty funny.
Actually got that part right.
Okay, so let's move on. Okay.
Yeah.
Fast forward. There we go. Okay, so the first one talks about endianness, and that's not even in assembly, so we move on to the actual assembly code. Yeah, this one is in assembly already, so it has to be this one. Okay, I think it's right here. So I wrote a kind of short and pointless program, and the only point of this program is to illustrate, how to examine memory locations. And the way I did it, okay, is coming here, right here, L1. Okay, so when you look into the debug session, I was using L1 as a bookmark and say, hey, give me or dump out the memory content at L1. So L1 is a very important concept. Is that label is what you're going to hold on to and say, okay, this is a reference point. Certain things are before, certain things are after, but they are at a fixed distance from where L1 is. So I'm hoping that's going to give you some idea of how to make this part. Sure. Question? Oh, you were just spotting a fly or a mosquito. Okay. Any other questions? Okay. Apparently, I forgot to talk about the indirect operand, or at least I did not demonstrate how it works. Did I?
You
only mentioned it.
Okay, so I did not actually talk about it. I thought so too. Okay, so we'll go ahead and take a look at that today. All right, I'm stopping the replay of the video on Tuesday, and we'll start to talk about the indirect operand. Before I talk about it, actually, discuss and explain the concept. The first thing I will do is to show you where you can find it. So in the class website, in the topics, when you go to topic, the topic for assembly language programming, These two links, will contain information about all of the addressing modes, including the indirect addressing mode, the direct addressing mode, as well as the immediate addressing modes. So those three are explained in both the older notes on addressing modes and memory organization, as well as addressing modes and memory allocation. These two, one is an older version, the other one is kind of like a newer version. I rewrote it, but they basically contain the same content. So if you just spend a little time to read about the addressing modes that we have been using, which would be the indirect addressing mode, the direct addressing mode, the immediate addressing mode, and also the register addressing mode, those are the only four that we have talked about up to this point. Okay, so that will give you some information or something that you can read on. We kind of talked about the other ones already, and I think the indirect addressing mode is the only one that I have not talked about. So what we'll do today is I will write a sample program to illustrate that concept. Okay. So I'll just call this program indirect.s and .text, which is redundant, okay, because that's the default to begin with. .global_start. So today I can just kind of talk a little bit about what is .global start. .global start is kind of the same thing as an extern in C++ or in regular C. An extern in C and C++, does anyone remember in your CISP 360, what does extern mean? Go ahead, George.
That variable is defined in some other file outside of this.
Right, so it's basically saying, okay, it's from somewhere else. But in this case, it is actually can mean both. Okay, it can mean that it's from somewhere else. It can also mean I'm exporting it. In other words, when I define _start here, it will export that so that it's visible to the linker. No other label, if you don't say .global, okay, when you use labels in a program, it's not going to be exported. In other words, L1 in your homework assignment is not going to be available to the linker. The linker does not even see L1 whatsoever. Okay? But _start is special. _start is special because it defines the entry point of your entire program. Okay, let me illustrate what I mean by that. I can put instructions before this, okay? With L, $1 to EAX, or whatever, okay? And then I can put instructions over here. This is the exit code. I'm just going to put in the exit code, which I will not explain until a little bit later in the semester. Okay, so when I have a program like that looks like this, I actually have 4 instructions in this particular program, right? The first instruction is on line 4, okay? But that's not the entry point of this program. I don't want that to be the first instruction to execute of this program. Now, I understand this is the same thing as the other one, so I'm just going to use another instruction here. Okay? We will eventually get to all of these instructions, but I'm just using it as an example. Okay, so line 4 and line 5 is for something else. Okay, but I want the entry point to be line 7. The linker does not inherently know where to start the execution of the program. So that's the purpose of the _start label, because that is a marker to tell the linker, which eventually will produce the executable, and say, hey, this instruction is the very first instruction. This is the entry point of the entire program. Is that okay so far? The purpose of _start. It's the same thing as main in C and C++. Yep.
Does that mean everything prior is treated as like a pre-processor directive almost?
You mean line 4 and line 5?
Yeah.
No, they're really just code, sitting out there. Okay. Eventually, they can be executed. If I call a subroutine or jump into those locations, I can still execute those instructions. But I don't want those to be the first instructions to execute. So this way, I can put the actual entry point of the program anywhere I want, because _start marks the entry point of the entire program. All right. So with that out of the way, we are going to just illustrate the whole concept of indirect access. So I'm going to use a dot word here, and we'll go ahead and say 0x ABCD, 0x 1 2 3 4. That's it. That's all I'm going to do. I will use an instruction like this. Okay, move EAX into EX here. Okay. And well, just to, as an additional help to your homework assignment, I'm just going to make this one, resemble a part of what you have to do with your homework assignment. So what if I want BX to have this particular content when everything is done? So I want BX to have, I don't know, let's see. Okay, so I want BX to end up with the content of in hexadecimal 34AB. Okay. And I have yet another instruction before that to initialize EAX. Move L dollar blah 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 into EAX. So I'm hoping this is, you can see that this is bearing a little bit of resemblance to one part of your homework assignment. Okay. All right, so let's find out what line 7 is really going to do, because line 7 is not the line that you can change, but you have to understand what it is actually doing in order to accomplish the actual objective. Line 7 is saying, I will use the content, the value stored in register EAX, and I will eventually dump that bit pattern onto the address bus of the system. And then I would use whatever content is at that location in memory and copy 16 bits from memory to register BX. You had your hand up first, and then it will be next, and then back here. Yep.
In that line, what's the purpose of the parentheses?
The parentheses is important because without the parentheses, it is a register operand, which means I'm just copying from a register to another register. With the parentheses, it becomes a indirect operand, which means I am dereferencing the register as if it is a pointer.
Don't you need a label?
I actually don't.
Okay.
I already have one. Do you find any colon in this code here? Because the colon is the designation of a label definition. Yeah, I do.
Oh, after start?
Underscore start, right? Well, that gives me one reference point.
Okay.
That's all I need.
I didn't know you could go with that.
Oh, any label would serve as a reference point.
Okay.
And there was another hand somewhere.
You pointed at me, but I didn't have my hand up.
Oh, okay, all right. Yep. It
So-
must be George then.
Yeah, basically. So those commands are just dumping a series of bits into memory locations from start. So they're just dumping like content. So start as being a label. The very first bit of like the first byte from start would represent move L blah 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 that command, right?
Correct.
So if we wanted to hypothetically get to line 11, it would just be incrementing how much ever from the start point.
Correct. Yep. Yep. Because everything can be relative to a label. So I just need to know the relative distance from the label underscore start to get to everything in this particular program.
So then the next question, no, I guess that's fair because, okay, I'm sorry. So then from start, move L, we said a long that's a long word, so that's what?
32 bit.
32 bits, so 4 bytes.
Uh-huh.
So from start, there's 4 bytes that take up that expression.
Not quite. The instruction move L dollar something to EAX is longer than 4 bytes because it's just like the instruction that we have with our own architecture.
Yeah.
Remember the load register instruction, where the instruction itself is 1 byte, but the next byte specifies the actual value that you want to copy into a register. Move long with an immediate operand is exactly that. Okay? Because you are just copying whatever the expression after the dollar sign is, you're copying exactly that value into register EAX. So it is exactly the same as that particular instruction of our own toy architecture. Okay. the indirect concept. Are there any questions about the indirect concept? Go ahead.
So if we don't have parentheses on line 7, then?
On line 7, okay, what was the question?
If you don't have those parentheses, then what will happen?
If you do not have those parentheses, the assembler would actually complain in this case. Because what is the width of EAX? 32 bits. And what about the width of BX?
16
bits.
They're not compatible. So the assembler would definitely complain about this one. Besides, the instruction itself, move W. What is the W suggesting? It's a word which is 16-bit. Okay. So now we have a disagreement between the opcode itself and the operand, which is the one you have to specify in addition to the opcode to do something. So when there's a disagreement like that, the assembler will complain and say, this program cannot be assembled. Okay. But the indirect is okay because the indirect is just saying it's a pointer. You can have a 32-bit pointer pointing to a 1-byte thing, a 2-byte thing, a 4-byte thing, an 8-byte thing. Doesn't matter, right? Because the size of a pointer does not imply the width of the thing that you want to point to. And it's the same thing here. So I'm using a 32-bit pointer as EAX to point to a 16-bit or 2-byte thing, which is the 2 bytes that I want to copy into BX. Okay. The way I use EAX in the instruction on line 7 is the same thing as the indirect register in the toy architecture that we have been using for the past, 8 weeks or so. Okay. Eventually, what would happen is the content of EAX, which is 32-bit wide, will be driving the address bus to the memory, and as a result, EAX is actually serving now as a pointer because it is specifying the address in memory, and then the content at that location in memory will be copied. 2 bytes starting at that location will be copied to register BX. Are we still doing okay so far? Okay. So what we'll do is we'll start with something that is completely unreasonable, and we'll see what happens. Okay. We'll just say, okay, well, we'll do something like this, or something that's even a little bit better. Okay. Because the objective is to get 34AB into EBX. Maybe if we copy that into EAX, then the instruction on line 7 will copy that in return to BX. Okay. Well, that's not going to happen, right? Okay. Okay. Let me just give you the equivalency code. The equivalency code is something like this. EAX gets exactly the value of 34AB. And then the second one is saying BX as a word, as a short integer, is getting that. So I'm casting EAX, because registers do not have types. Now, if they don't have types, they cannot be used as a pointer, right? So that's why the first thing I do is to say, hey, let's look at EAX as a pointer. That's what the pointer cast is about. Okay, they're just saying, let's pretend it is a pointer, or whatever the content of EAX is an address of a short int. Then I can do the dereference. So the asterisk of, okay, let me just point out which one we are talking about. So this asterisk is basically a dereference operation, right? So I'm dereferencing the pointer, which is basically EAX, and say, oh, go to that location pointed to by EAX, give me 2 bytes, and what am I doing with those 2 bytes? Well, this is an assignment, right? So whatever I specify on the right-hand side is copied to the left-hand side. So BX ends up with those 2 bytes in memory, pointed to by EAX. Okay? But this program obviously is not going to work, because what I'll do is I'm going to memory location exactly 34AB, which is not a location that your process can access. A process is a program in execution. Okay? The amount of memory that your program can actually access is very small. Okay? And that's not one of the locations. But I do want to show you how this program is going to crash, because the way it crashes will give you a clue of what is happening, and it will help you debug the program. Okay? So we'll go ahead, knowing this program is not going to work, we'll still go ahead and assemble and run it, just so that we can see the error message from GDB. So ASGstats-O indirect.O indirect.S LD indirect O GDB indirect. All right, so what we'll do is we'll run the program just at full speed, okay? Well, maybe not. Maybe we'll just kind of put a breakpoint on line 7. Run the program. Line 6 has now executed. So I can look at EAX and in base 16, and that's expected, okay? Because I did copy the value 3480 into register EAX. The next instruction, when I single step the next instruction, it crashes. Okay, it gave me a segmentation fault. Program received segmentation fault, and it's complaining about this instruction. It says this instruction is generating a segmentation fault. A segmentation fault always is because of accessing memory, where you're not supposed to. BX as a register is not memory. So the problem can only be coming from the first operand, which is an indirect operand. So, but because it's an indirect operand, you can always look at the register and find out which location it was trying to access. In this case, it is location 34AB, which is not a typical location where you can access. Yep.
And how do we? Is it that that bit of memory that each process gets? Does it theoretically start at 0 and goes to a certain size?
Nope.
Or?
Well, in terms of logical space, it starts with 0, but in terms of where your program actually starts, it's not 0.
Yeah. So, but as an actual value, that's just some decimal number that's saying that's far larger than the actual space that was given.
Absolutely. The actual location of the PC. Do you still remember the program counter from the architecture that we talked about? If you do an IR, which is info register, it shows you all the registers, and EIP is our instruction pointer. In other words, EIP, which is extended instruction pointer, is our PC. It's just a different terminology used by Intel, but it is the program counter, and that's where the program is, which is a completely different type of number compared to 3480. Are we still doing okay so far with this code?
Does that start +5 stating that's how we got that value? That it's from
It is 5
start.
bytes from the start label, which is handy. Which is handy, right? Yep. All right. So are we still doing okay at this point? Sort of, maybe. Okay. Are there any questions before I move on? Because if you have any questions, this is a good time to ask.
These are all registers?
These are all the registers, and many of these cannot be accessed directly as a register. If you remember, our own architecture has a whole bunch of registers too, right? We have the registers ABCD, which are accessible by instructions. We also have certain registers that are not directly accessible by instructions, like the microcode counter. Okay, the microcode counter is not here. That one is completely not accessible. But the indirect register is one of those. And then what else do we have? We have the program counter, the indirect register, and the instruction register. The instruction register is not here either. Okay.
How would we consolidate what we were playing with like so for ROM? How could we get that to be with? Because here this is dealing with RAM itself, like the actual
That is
RAM
correct.
chips.
The microcode engine is completely invisible to you in GDB as far as the x86 processor is concerned.
So we could think of like how, whereas we were implementing opcode inside of our ROM, we could think of all that in this world existing all in RAM at the same time.
No, it is just invisible. The entire microcode engine is invisible from this perspective. Because no one who's writing software or programming really needs to know the microcode part of a processor, because you can't really change or control that part anyway. But instructions is important for us because we are, after all, writing instructions that will be running from RAM, and that's why only this part is visible to us from GDB. Yep.
Will we be using most of these?
No, we'll just be using registers A, B, C, D, E, B, P, and then ESP. So 6 of these registers will actually be used a lot. The other ones, we are not going to use.
Flags, you don't use the flags?
Hmm?
You don't use the flags?
The flags will be used, but we are not going to use the register. We'll use individual flags. Yep. All right. So if there are no questions about the program, or why it crashed, let's go ahead and change the program a little bit, and so that we can solve the problem. Okay. So what I need to do here is not the content of what needs to go into BX, but the location of that content that goes into BX. So the first thing we need to do is to find out how memory is actually laid out with this particular .word directive. Now, when you are trying to figure out how memory is laid out, you have to remember memory is organized byte by byte, because the i386 architecture is byte addressable. Every byte has its own address. So when you're dealing with anything that has more than 8 bits or 1 byte, like a .word, a .int, or anything longer than 1 byte, then you have to remember little endian, okay? Because what it means is the least significant byte has the lower address. So now we will go ahead and take a look at how memory is laid out here. CD goes first because it is the least significant byte of the first .word thing. AB goes next because it is the most significant byte of the first .word. Then the least significant byte of the second .word, which is 3-4, goes next. And then 1-2 is the last one because it is the most significant byte of the second .word. Are we doing okay so far with this? Attack, I think the homework assignment cannot be done because we want 3-4-AB to be in BX. I see AB, I see 3-4, but they're in the opposite order. But remember, when we look at the value of BX, we are looking at it as a 16-bit number. In other words, when we spell out 3-4-AB, 3-4 is the most significant byte, and AB is the least significant byte. And then when you combine that with little endian, then everything should make sense, right? Because AB is actually the least significant byte, occupying the lower address. 3-4 is occupying the higher address. Okay, so we know which 2 bytes we want now, right? Because we want these 2 bytes to be copied into BX. Now the next question is, where are they? Well, underscore start is immediately after these 4 bytes. So you can look at the last byte, which is the 1-2, as underscore start -1. 3-4 is -2, and then AB is -3. Yep.
That global start doesn't signify that the .word stores those bytes after start?
It doesn't matter.
That one's the bookmark.
So that's the bookmark.
Yeah, the first one is your bookmark, and then the other start.
And the second is your bookmark.
Yes.
Yeah, that's what he said.
Well, that's what I meant.
He means the first instance of start.
The one with the colon.
Yeah.
That's the bookmark.
Yep. When you define a label, you put a name there and then the colon to indicate this is where I want to define the label.
Oh, okay. So all
This
we
would
do
be the start.
Yeah, so 2 just declares it, and then line 6 actually defines.
Line 2 is just saying, okay, the linker may need to know about
Yeah,
this.
it's just a
That's all it
declaration.
says.
Yeah, it's just like a declaration of start.
Yep, exactly. So what do we need to put after the $sign on line 6? You had a question?
Go on. I think you're about to answer it.
Okay. So what do we need to specify on line 6 after the $sign? Well, with this one here, okay, as long as it is for educational purposes, I don't mind if you guys just try out different things. Start out with underscore -4 first, okay, see what happens. And if it's not what you want, you kind of have to explain that, okay? Why is it close but not exactly what I want, okay? So I'm not going to give you the direct answer because I kind of spelled it out earlier already when I counted -1, -2, -3, and so on. But I want to give you this, and and you can run through the debugger. It's not going to give you the answer that you want, okay? But it gets close, and then you have to be able to explain oh, it's not quite exactly what I want, but let me see why it is not what I want, and how do I change it so it becomes what I want. Okay. So is that helping out with that one piece of the puzzle? Yep, go ahead.
Is there a way to print out something not using a debugger?
Is it to print out? What
To
again?
print out like cout, like. Is there a
Oh,
way
in the assembly code?
Yeah, the assembly.
Nope. we are quite far away from being able to do that. Yep. Because this is assembly code, and we cannot call a subroutine. Cout is actually a fairly complex call in C++ because it's object oriented. Okay. So let me test your knowledge in C++. Okay. What is cout? Not the type. Okay. But what is it? Is it a function? Is it a class? Is it a variable? Is it a what is it?
It's an object.
It's an object, but since it has a name, it is a class.
A string? No, cout is a string.
That's the type. That is the type. That's which class it belongs to. It's not a function. It's a variable. It's a global variable. Cout is actually a global variable, which is an object of the output stream class.
Okay.
Okay, as opposed to printf. Okay, what is printf? Printf is just a regular function. That's all it is. Yep. It's a global variable.
Global variable, but it's an object that's a global variable.
Well, every variable is kind of an object. Okay, but then you have objects that has no name, where you only can access it by a pointer, and then objects that are directly accessible by its name, and those are your variables. Like local variables and global variables, those have names, and that's why you can say which one you want to use right away. And when I say cout, it's not complete either, because I should have said std::cout, because that's the namespace where cout belongs to. Right. So are there any questions about this particular program? Are there any questions about how this relates to your homework assignment? Go ahead.
I think you had already answered this, but when it tells you that EAX or EBX should store the value and then LSAT 388 whatever, is that in little endian format or is that in big endian format?
When you spell out a number like the comment on line 8, it is the usual way of writing a number.
Okay.
So 3 for AB is 3 is the most significant digit and B is the least significant digit, just like you write any base 10 number.
Okay.
When we spell it out on line 3, okay, with a space in between, this is when I try to lay out the memory content. So that means CD has the least address, has the lowest address, and 1, 2 has the highest address. So that's why I intentionally use a space to break it up, so that this way, it is fine. This is a memory layout instead of reading it as a single.
And in the assignment, you're specifying reading out regularly, not in
Correct. Everything in the homework assignment is read out as a number.
Okay.
So the leftmost one is the most significant digit, and the rightmost one is the least significant.
Thank you.
Yep. Because the whole point is to make you guys think about how we write a number and how it is actually represented and how it's laid out in memory. And how there's no such thing as the border between two things. Because when you look at this one, the 3-4 comes from one dot word, and then the AB comes from the other dot word. Now you would never imagine doing something like that with variables in C and C++, right? I want to get half of this variable and then the other half from here, okay? Well, you can do it with bit shifting and all kinds of other tricks, but not something like this, okay? This one is saying there's no such thing as a boundary between constructs. There's really no such thing. If you want to, I can grab 1, 2, and then the first byte of the move L instruction and put it into BX. You just have to specify _ start -1 on line 6. Then we'll be grabbing 1 byte from the second dot word and then the first byte of the move L instruction itself. There's no boundary. Memory is completely contiguous. It's just byte, 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 and any type of boundary is really just enforced by your own code, and the system does not really have any inherent boundary. Yep.
Things like dot long, they only give it 1 byte.
It will be using 32 bits to
Yeah.
represent the value that you use 1 byte to write.
Now it's a pad 0.
Well, it will have whatever it needs to be padded in order to represent it. Okay. Now, I said it that way not to make it intentionally make it more obscure, but because it is actually necessary. What if I have a dot long and then I say -1, -1? Yep. Well, but every single value will use all of them.
Yeah,
Okay.
but I mean, but there will be one in all of them except for the least significant bit.
If I specify something like this, then it looks at this as the value that needs to be represented. It looks at this and it will say this is how many bytes it will take. So how do you use 32 bits to represent the value of -1? Now this goes all the way back to 2's complement, right?
2
Yeah, 30.
You will have 32 ones, right? 32 ones. I think in the assembler, you can actually specify base 2 by using 0t as a prefix of binary. So you can say 0t and then give it 32 ones. You can also say 0x FFFF, FFFF, 8 Fs. You can say -1 as a signed base 10 number. You can also say 4 billion something as an unsigned value. So all of those will give you the same bit pattern, which is 1111, 1111, 1111, basically 32 ones. Okay, so that was a good question, and this is the explanation of why I said what I did. So if you give it a 0, it's the same thing. Okay, it's basically saying this is the value that you want to store using 32 bits. So how do you represent 0 using 32 bits? It will be all 32 zeros, right? So that's basically what it is. Right, so I'm kind of glad that we clarified quite a few things. And are there any other questions that you guys want to ask about the homework assignment? Is that helping? I mean, this is the missing link. This is the one about the indirect operand. Okay, no questions? All right, if there are no questions, we are really kind of done with operands or addressing modes. There are 12 more. Okay, the Intel architecture is called a CISC architecture for a reason. How many people still remember what is CISC? C-I-S-C. What is it?
It's when you have way more instructions, but you lose a lot of something.
Okay, so but the name itself is complex instruction set computer. Okay, which means the instruction set itself is complex. It is very rich. It can do a lot. Okay, and that's what it is. Okay, the Intel architecture gives you 16 addressing modes. We have talked about 4 of those 16 ones. Okay, so the 4 that we have talked about, they're not all in here. We have direct, indirect, immediate, and register. Those are the 4 that we have already included in the homework assignment. And then the other 12 are variants of these things. So it would be, if you want to remember the names, they're all written in the notes. So there's based, and then there is based indexed, what is the other one? Scaled, indexed scaled. I'm just gonna cheat and look at my notes. All right. These are the 16. Well, there are only 10 of them. Okay, so there's immediate, register, direct, and then indirect, and then there's the other addressing modes. Okay, there are 8 of them. Sorry, I take it back. There are only 8 of them, and then we are only going to use 4 of those 8. Later on, we'll be using the base addressing mode because of convenience. It really is making a lot of things a lot easier. But at this point, we are not going to talk about it. We're not going to use it. We'll just be focusing on the 4 that we have talked about. So this is it. This is we are done with the move out instruction, the copy instruction. Yep.
In RISC architecture, is it only 4 or is it fewer?
Within the RISC architecture, they would typically have the indirect operand, where you can use one register as a pointer, because this is the only way you can control which location in memory you want to access. So that one is mandatory. You must have that. The other one is register operand. That one is a must as well. You have to be able to get the content of a register or to put some content into a register. So indirect and register are completely mandatory. Immediate is useful, but it's not 100% necessary because you can have direct and not have immediate. So every constant that you will ever need to use in your program, you can keep it in some initialized locations, and then you can use the direct operand to say, oh, I want that constant value. You just copy it from that location in memory into a register. So of those 4, you only need 3. The 2 that you must have would be indirect and immediate. Excuse me, take that. Immediate and register. And then between immediate and direct, you can have one or the other, because they can, with one you can implement the other, combined with the 2 mandatory. Yeah. But typically you will find all 4 with most common RISC architectures. That's a good question. All right. So now we are really quite done with addressing modes. So this one and this one is now all done, and we can now move on to arithmetic operations. And this is basically old stuff. We have seen it already. We just haven't seen it in the form of instructions with the i386 architecture. So when you look up this node here, we have pretty much talked about base conversion. We have talked about binary addition. So when you look up this particular binary addition, we are just repeating all the stuff that we know already. Okay, 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1, and 1 plus 1 is a 0 with a carry. Okay, stuff that we already know when we talked about half adding and stuff like that. And this one is just a demonstration of how to do binary addition by hand. Okay, it's completely, well, not completely, but it is step by step to a certain extent. Stuff that we should know already. Okay, so if you are kind of shaky about this stuff, you might want to kind of review what we have already talked about before this. Okay. I'm going to close off the tabs that I don't need. Where am I? I'm losing track. Right there. Okay. So we talked about addition, we talked about subtraction. So when you look up subtraction, same stuff, stuff that we have talked about already. 0 minus 0 is 0. 1 minus 1 is 0. 1 minus 0 is 1. The only one that is kind of tricky is 0 minus 1. So 0 minus 1, usually you call it -1. But if you want to stack your subtraction, to multiple bits, then it's best to call 0 minus 1 being 1 with a borrow of 1. Okay, so that's also stuff that we have talked about before. Nothing new. And then there's a completed example of bitwise subtraction. So once again, nothing really too new here. And then we have negation. Negation is 2's complement. Okay, so basically 2's complement is the bitwise not, which is also known as 1's complement plus 1. So basically stuff that we have talked about already as well. Are there any questions about any one of these? No questions? All right. If there are no questions about this, we'll move on to the next one. So we'll go up, back to binary. Signed versus unsigned interpretation, that we have talked about as well. And then we talked about flags. Okay, we talked about these 4 flags already. In fact, your homework assignment is about these 4 flags. Okay, the 0 flag means everything is 0. All the bits of the output of an operation are zeros. Okay, the number is 0. Carry flag, which is also the borrow flag, means you have a leftover borrow or carry of 1 after a subtraction or an addition. Negative flag, or the sign flag, is the most significant bit of the result. And then the last one is the overflow flag, which is the more complex one, because that one is a 1 whenever the sign of the result does not make sense, after an addition or a subtraction. Okay, so the status flags are stuff that we have talked about already. And then there's the interpretation of the flags. Okay, that's basically stuff that we have talked about already as well. So now we take a look at the instructions. And the first one is the add instruction, and also the add with carry instruction. The add instruction, just like the move out instruction, has 2 operands. The first operand is a read-only operand. The second operand is a read-write operand. So it stores the result as well. And the best way to illustrate this is to give you an example. So we'll take a look at this particular example here. It's an add-out instruction. We are basically adding the number in EAX to whatever is at large num2. In this case, I'll just give you a quick quiz here. What is the addressing mode of large num1? You get 4 choices. Is it a indirect operand? Is it an immediate operand? Is it a register operand? Or is it a direct operand? It's not a register. It's a direct operand. In other words, it does access memory. Large num1 is large num2. Large num2 is the label, which is the address, right? It's a bookmark of an address. Without the $sign, it is not immediate. In other words, we are going to add whatever EAX has to the 4 bytes already at large num2. So those 4 bytes in large num2 will actually get changed as a result. Okay. Now, in the earlier part of this program, there's a .field directive, which we have not discussed yet. .fill is basically just saying you fill with 0. In this case, it will fill it with 8 zeros. It will allocate 8 bytes exactly, and then every single byte is a 0.
Fill works with bytes, not with bits. It's bytes, so it's 8 bytes.
It will allocate 8 bytes, and all 8 bytes will be zeros. All right. So let's go ahead and take a look at a simpler example, okay, without the use of memory and stuff like that. So let's go ahead and write add.s, and we're not going to even mess around with memory because we can just deal with this using immediate operands. So we'll go ahead and move byte $23 into AL. Okay, so I'm dealing with 8-bit registers here, and we'll just go do an add byte, and we can specify another number here. I want to specify something that's a little bit interesting. Well, let's not get too tricky yet. Let's do a 110 to AL, and then we can do the exit code thing, which is move L $1 to EAX. It's not important because we are not going to even get to that point. Well, I'll stop the debugger before we get to the exit code here, but I'm just going to specify. All right. So we'll go ahead and try out this program and find out what it's going to do. But it does several things. Okay? Line 4 is pretty easy. We're just copying the value 23, or the bit pattern representing 23 as a value, to register AL. Register AL is which part of EAX?
The lower bit.
Yep, it's the least significant 8 bits of EAX. Okay. So only that portion will be changed. The rest of EAX will still be the same as before. If it has garbage before, it will still have garbage. Only the least significant 8 bits is going to be changed. Then we're going to add the binary representation of 110 to AL. What do you think AL should end up with? That's a trick question.
23.
It's not going to be 23. Okay, so the two answers that, okay, there are two possible answers, right? The first and the most obvious answer is it's going to be 133. Because 23 plus 110 is 133. But there's an opposite side to that. Because 133 is more than 127, which is the last positive number you can represent when you're looking at 8-bit as a signed number. So this can also be a negative number. Okay? Now how negative it is, or the magnitude of the negative number is 256 minus 133. So that would be what? 122. So it would also be negative 122. Okay. So we'll find out, but what is GDB going to print? If I were to say print AL, $AL, will it print it as the signed, using the signed interpretation or the unsigned interpretation? Well, we'll find out. Okay. Well, GDB can do both, because print can take a slash, which is the format. So you can print it out in hexadecimal. You can print it out as a base 10 signed, base 10 unsigned, binary, or as a character. Okay, if it does match a particular ASCII code, it can print it out as a character as well.
But no, I was saying like the initial print with no format will be the default of whatever.
The default
GDB
is going to be
decimal.
a signed decimal representation. So it should print negative 122 without any slash, without any format string. So we'll go ahead and give it a try. AS-G stats-O add.O add.S link GDB add. And we'll put a breakpoint on line 4. Okay, run the program. This is before line 4 executes. So we'll go ahead and say print AL, and AL is 0. Okay, the 8-bit register is now representing the value 0. No big deal. Single step, it is now representing 23. Okay, kind of expected. This is the tricky one. Okay, now we have added the bit representation, or the binary representation of 110 to the binary representation of 23. And we say print AL, and it's okay, I'm off by 1. Okay. But it is because I do the subtraction wrong, because I said 256 minus 133, but I got the math wrong. I thought it was 122, but it's actually 123. Okay. But this is because it defaults to a signed base 10 representation. You can force it to a unsigned interpretation. I can't remember exactly how to do that. I think it's just U. Okay, yep. You can see here, U is unsigned decimal. This is actually the convention used by printf as well. Yep. So it's consistent with the way printf works. So if you specify a slash U, it is 133. Not negative 123. Is that okay so far?
Can you try to print it as a character?
Well, ASCII does not have, does not go that far, so it cannot do it. And if it cannot do it, it will just print it out as a backslash, and then the octal representation, because that's also how you can specify any character in a string when you're dealing with C. Yep.
So let's say you wanted to add whatever's in AL to a different register, for example.
Yeah.
Would it use negative 123 or 133?
It's the same bit pattern. It doesn't matter. When you print it out in binary, you will see that it is the same bit pattern anyway. Okay? So this is getting back to when you look at these 8 bits, okay? 1000, 0101, what is it? We don't know. It can be representing negative 123. It can be representing 133. It can be 8 pixels of a black and white picture, right? So we have white pixel, dark pixel, dark pixel, dark pixel, white pixel, dark pixel, white pixel. It can be 8 individual bits. Okay, it can be representing, oh, the first sector of the disk is in use, the second one is not in use, the third one is in use, and so on. So by looking at these 8 individual bits, it's like, well, we can interpret it in many different ways. I have no idea what it is.
Okay.
Is that okay?
Yeah.
Yeah. This is one thing that you have to remember in this class is in C and C++, everything has a type. Okay? Whenever you use a value, a constant, whatever you do, whatever you use in a program has a type associated with it. Assembly language programming is the exact opposite of it. Nothing has a type. Everything is just a bunch of zeros and ones. Now we do have certain ways to organize the zeros and ones. We group 8 zeros and ones into a byte, and every byte has an address. Okay, and then we have the little endian organization. When you have a multi-byte value to represent, we use the little endian way to organize the bytes, but that's about it. Otherwise, zeros and ones are just zeros and ones until you need to do something about it. Okay? Are there any questions? Yep.
What happens when you add 2 numbers and it exceeds the amount of bits available?
That's a good question, and we have seen that already. Okay? Not overflow.
The flag.
One of the flags is going to be set, but not necessarily the overflow flag. The carry. When you're adding, is the carry flag. The whole concept of the carry flag is the quote-unquote leftover carry that has no place to go. And that's the one that will be set when the result cannot store the actual value, but that's using the unsigned interpretation. Okay. Yep.
Would the overflow get set if we were trying to add it entirely to EAX, because that's the size of the machine, and therefore that would be an overflow?
Even this instruction will set it if it is the right condition. So every add instruction, whether you add byte, add word, or add long, will affect all 4 flags the same way. It's just which bits is it paying attention to. If you're doing add byte, the most significant bit is now bit 7. If you're doing add word, the most significant bit is bit 15. If you're doing add long, then the most significant bit is bit 31.
And then that does affect the overflow.
Yes. Well, talking about the overflow flag, should we get an overflow in this case? We just added, Yep,
Yes.
we added 2 non-negative values and we ended up with a negative value under the sign interpretation. So the overflow flag should be set. Okay? Yep, we can. But I want to talk about all the other ones first, okay? What about the 0 flag? Should the 0 flag be set or not? It should be clear because the result is non-zero. How about the carry flag?
Yes.
The carry flag is, well, we did not roll over after 255, so the carry flag should be off, okay? And what is the last one? The sign flag. The sign flag is off or on?
Yeah.
Should be
It should be set.
on, should be set because bit 7 is set. Okay. Well, how do we know bit 7 is set? Because it's being displayed right here. It's staring you in the face as we speak. Okay, so let's go ahead and check out the flags. The flags are in the register called E flags. And it is kind of obscure because it will only confirm which flag is set and it will not tell you which one is cleared. Okay? So in this case, there are also other flags that we don't care about. Okay? AF is something that we don't care about. IF is something that we don't care about. But sign, the SF is the sign flag. It is set as expected. OF is overflow flag. It is also set as expected. ZF is 0 flag. It does not appear because it is cleared. And then the carry flag is the same way. It is not seen here because it is cleared. So are we doing okay so far with this stuff here? Are we making links between what we are talking about here to stuff that we have talked about maybe 4 to 6 weeks ago? Okay, very good. I'm glad that some of you still remember stuff from several weeks ago.
It's tough. There's been a lot.
Hmm? There's no escape from it. All right. So are there any questions about the add instruction? No questions? All right. So if there's an add instruction, why do we need an add with carry instruction? Well, first let's talk about what is the add with carry instruction. The add instruction is just adding the first operand to the second operand, and then the result is stored in the second operand. Okay? The add with carry instruction has 3 components. There's the first operand, there's the second operand, just like a regular add, and then there's the carry flag. So the carry flag is representing the third number, and then the 3 will be added. The result will always be stored in the second operand. Are we doing okay so far? But what can the carry flag possibly represent? Which values can the carry flag represent? Since it's only 1 bit. It's 0 or 1. Exactly. So it's just a 0 or 1. So why do we have that odd instruction called add with carry? Why do we care about the carry flag in an addition instruction?
You know if it exceeds the storage value.
But who is exceeding that makes it necessary to add with carry? You're definitely on to the solution.
Who is exceeding it?
Yeah, who did not have enough bits to represent the end result?
The register.
The register or whatever the second operand is, right?
Yeah.
But not of the same instruction. It's an early instruction that ran out of bits. Okay, so what we want to do is a multi-byte addition. Okay. Let's go ahead and think about this way. If you just think that this architecture is an 8-bit architecture, all it can do is to add bytes to bytes. Okay, which is not unreasonable because many years ago, when I said that it's like 40 or maybe 30 something years ago, processors only have 8-bit ALUs. So all they can do with one single instruction is to add or subtract 8 bits. That's all it can do. But even back then, people have need to deal with 16-bit numbers, right?
Yeah.
So how do you stack up add instructions so that they can, with multiple instructions, you can do multiple byte adds?
The carrier says it's not done, and they keep doing it.
Yep, exactly. Okay, so let's take a look at this picture here. Okay, so we have each box is representing an 8-bit quantity. Okay, I want to perform an addition. Okay, now we kind of know the general routine of doing this, right? The bottom row is going to be all the carries, and the least significant bit always has a carry of 0 because there are no digits prior to that, right? So we do the usual stuff, okay? And out of this particular column, there will be an extra carry that goes into the carry flag. But this entire thing is done by one single add instruction. It's just a regular add byte instruction, okay? But the second instruction is for the most part the same thing as a regular add instruction, with only one exception. I don't want to assume there's a 0 here. I don't want that, because who should be here?
Carry flag.
The carry flag from the previous add byte instruction. Exactly. So I want whatever carry flag is coming out of the add byte instruction to be here. And that's why we have the add byte instruction. Add with carry instruction. ADCB, add with carry byte instruction. So this is ADB. It's a permutation of the first 4 letters, and that's why it's hard to get it right. Okay, so add with carry byte, ADCB. Okay. Are there any questions about the necessity of a add with carry instruction? why it is necessary. But tech, that's way in the past. I mean, this is the Intel processor. It's a 32-bit processor. So why do we have to deal with this? Because now we can say, hey, this is a long, right?
Yeah.
32-bit add and 32-bit add. Who needs to deal with 64-bit numbers? I mean, that's like completely bogus.
Someone does. If it's for processors.
Well, if you want to represent the national deficit, you need it. Because what? It's in trillions, right?
Yeah.
So trillions would be thousands of billions. So you'll be using up definitely, you need more than 32 bits.
If you want to measure an atom.
Well, then you need floating point numbers and stuff like that. Yeah. But 64-bit numbers, by today's standard, is common. Okay, there are many places where you need 64-bit numbers. Okay, but tech, you are so old-fashioned. Okay, you're still using the 32-bit operating system. Everybody else has moved on to 64-bit operating systems. So that means each one of these is now a add Q instruction because it is now specifying a 64-bit quantity. Who will need a 128-bit integer, right?
I'm sure eventually.
We're getting
Astrophysics.
Astrophysics or well, I will tell you why. I will tell you what needs to be 128-bit. What is the result of multiplying two 64-bit numbers?
something that's going to be larger than 64 bits.
It can be up to 128 bits, right? Okay, but we are not going to deal with 128-bit numbers because when we multiply a 64-bit number with another 64-bit number, maybe eventually we'll still be dividing it by another 64-bit number, right? But even so, in the process of doing that calculation, you still need to represent a 128-bit number. Because you don't want to group the division first, you want to group the multiplication first. Let me tell you what I'm talking about. Okay, so let's go ahead and specify in64_t, which means 64-bit signed integer, and A, B, and C are all of that type. Okay, I want C to be A times B divided by C itself. Okay, so let's make it D. So D is the result. Okay, I want to get the product divided by C. Now you can say that in mathematics you can move the association, you can move the parentheses. You can say I can do the multiplication first. In a math class, you can also group it the other way and say that I want to do the division first. Okay, the math professor will say it doesn't really matter which one, because of the associative law of multiplication. But in this class and in any programming class using integer arithmetics, it does make a huge difference. Because what if B is a lot smaller than C? You end up with a 0. But when you change the order of the operation, it can significantly change the actual result. So that's why when you're doing calculations like this using integer arithmetics, you definitely don't want to group B and C or the division first. You want to group the multiplication first, so you end up with more digits of significance. Then you do the division, and this is the same trick as what we did with the floating point number conversion, right? Nightmare. But that's the reason why we are doing this, okay? But if A is 64-bit and B is 64-bit, the product can easily be more than 64-bit or requires more than 64-bit to represent. So that means we do have needs to deal with 128-bit numbers when the common integer type is 64-bit type. Are we doing okay so far with this? Okay, and that's why these instructions continue to be useful because it gives you a way to extend out your instruction set and be able to deal with wider integers with very little overhead. Because now to deal with twice the width of your native width of your ALU, you just need one more instruction. That's all. And that's dirt cheap, okay, when it comes to how many cycles you have to use. Now, what if we don't have add with carry instructions? We can still do it. But then you will need conditional branches and all kinds of crazy stuff. it would just be a whole lot less efficient when you want to do something like this. It can be done, it's just a whole lot less efficient. So in this particular case, the cisp architecture giving you this one extra instruction that is not 100% necessary actually makes sense. Okay, because it makes it so much easier to extend add and subtract instructions. Well, okay, subtract instructions the same way. You have SUB for subtraction, and then you have SBC for subtract with borrow, or SBB. Are there any questions about add with carry?
How does this determine when the carry flag is set?
Huh?
How does this determine when the carry flag is set?
It's done by the previous add instruction. Okay, let's go ahead and write an example to illustrate this one. Okay, so add with carry byte dot s here. Okay, so I'm going to use comment to indicate what I want to do. Okay, so what I want to do is to add 0x 12df to 0x 04. Well, a whole lot of numbers will fit this requirement. Okay, so we want to add these two numbers. Okay, and as the constants imply, they are 16-bit numbers, right? But I will try to restrain myself and only use 8-bit instructions. So I'm going to use add byte and that kind of stuff. Okay. So how am I going to do this? We'll actually go ahead and write this entire program. Global square start. Okay, so we'll deal with, okay, first question. Should we add the least significant bytes first, or should we add the most significant byte first? Least significant byte, very good. Okay, so let's go ahead and do that. In fact, the first thing we'll do is to move a W move both constants into registers, just so that it's easier to see the result here. So I'm going to move the first one into EBX, and I'll move the other one, 12df to register EAX, and we'll be adding. Okay, but when we do the add, we can only do 8-bit addition.
I'm sorry.
Yep.
Maybe I'm slow. But anyways, is there a pragmatic choice for which byte we choose?
You really only have one choice.
So,
well, okay, if you don't mind going through the scenic route, you can do it the other way, but then you will have to do something to fix something that you did earlier. Okay?
So it's
if
a
you don't
mistake to do that.
Right, if you don't want to go onto the scenic route and you want to get onto I-5 just to get to the destination, then there's one particular way to do it. Okay? So the first add instruction, can the first instruction be add with carry?
No.
Doesn't make any sense, right? Because the carry is a leftover by who knows whom, right? So we'll say add with carry, add byte without the carry, okay? And I want the result to be stored in EBX. Okay, so EBX is going to store the sum. Tell me what operands should I specify here? BL is the first or the second operand? Because when you add, you need to specify two operands, right? The first operand is read only, the second operand is read write, which means you are adding the first operand to the second operand, but you store the sum in the second operand. So we want AL to be the first one? Yep. And then we want BL to be the second one. That's the destination. And then with the next one, I'm going to say add with carry, because I'm using the carry flag from the first add byte instruction as this bit here. And we are now using the most significant byte, which is AH and BH. So by the time we get here, BX should be the sum of these two. So I'm going to do it. I'll try to do it by hand. So the 1 will still be a 1. Then we have a 7 here because of the carry. D plus 7 is 13 plus 7, which is 20. So then we have 4 as a leftover, but it has a carry from the previous one too. I think it should be 1750 in hexadecimal.
What if there's a carry in the first?
Take bets. Take
add?
bets.
There's a
Take it.
carry in the first add, what happens to it?
The first add will have a carry.
Yeah.
So let's document the first the first operation. Okay.
Does it have anything? You're not adding it to carry though, so what? Carry.
The carry will be in the carry flag itself. Okay, so let me document what happens after the instruction on line 7. So BL should end up with 50 in hexadecimal, and then the carry flag should be a 1. Right?
Yeah.
Because F plus 1 is 0 with a carry, and then we have D plus 7 plus 1. D is 13. 13 plus 7 is 20. 20 plus 1 is 21. 21 is 16 plus 5.
So that's a 0.
So that means it is a 5 with a carry of 1. And then after the second addition, BH should be 17, and the carry flag should be cleared because adding 4 to 12 to 1 will not exceed how much you can represent using the unsigned interpretation. Okay? All right, so let's check it out, right? And I need one more instruction here just to make it specify where to stop. We can put a no up here. And we'll assemble adcb.o, adcb.s. Warning, warning. Using there. I was using EAX and EBX, but the instruction is move W.
Oh, okay.
So that's why
16. They're just telling you
yep,
too much.
yep. Which is good because the assembler caught it. If I had used just move and not move W, then the assembler would have let me go. It would just.
It was using it, so meaning it just changed your code for me, right?
Truncated. It made the correction.
Yeah, it made the correction for you.
Yeah, it made the correction for me, but that may not have been my intention. Because my intention might have been to use the 32-bit register, and I just spelled out the instruction wrong.
Oh, okay.
Yep. So so whenever you get a warning, you really should be fixing it too. All right, so let's do the linking, ADCB, ADCB.O, and GDB, ADCB. Put a breakpoint on line 7, run the program, and the first thing is to double check register AX and register BX. Okay, no surprises here, right? Single step, and now we have to double check the theory. Because according to my theory, BL should be 50 in hexadecimal, and the carry flag should be set. So let's double check that. So print $BL, it is
No. Was that cool?
in hexadecimal, it is 50.
Not done yet.
Yeah. And then we want to check the E flags. And the carry flag is in fact set, okay? Now let's go ahead and single step, finish this operation. We'll check individual registers first. So we'll check BH. BH is 2323 in decimal. In hexadecimal, it is 17. So we got everything that's supposed to be here, but let's also check the flags. The carry flag should be cleared. It is cleared. Okay, very good.
What is that PF? Just for
PF is a half carry. So, there was a time when people care about a half carry, which is the carry flag from the first half of an addition to the second half. It's a partial carry, basically. IF is the interrupt flag, which is actually very, very important.
for IO device.
Nope, for everything, system-wide. So it basically says, can the system receive interrupts at this point? And it should be set most of the time. Yep. All right. So last thing to check. we want to look at Bx as a whole, and it does have the correct answer. Okay. Are there any questions? This is an example to illustrate how to use a single add instruction and then followed by an add with carry instruction so that you can extend the natural width of the ALU of the architecture. If you start with 64-bit, you can easily extend to 128-bit. And you can also chain more add with carry instructions after this. So this way you can extend from 8-bit to 16, 16 to 24, 24 to 32. Every single time you want to add the natural width of the ALU, you just stack up another add with carry instruction, which makes it very easy to extend the width of operation. Questions? It's all good? All right. Homework assignment? Any questions about that one? Well, I'll be at the lab, so in case you are working on the homework assignment, you got questions, I'll be at the lab. All right. I did not bring my roll sheet today, so no roll taking. No.
How will you know we were here?